Hi, my name is Thomas Sulper, and this is a presentation from the ASME Joint Fluids Engineering Conference that took place in August of 2019. It is a description of innovative equipment to mix and distribute molluscicide over expansive areas to treat zebra mussel infested waterways. And I'll start off with a little background on how it is that the problem arose and how it is that we contributed to efforts by U.S. Geological Survey to develop fluid machinery to solve that problem. So zebra mussels were first established or discovered in the Great Lakes in the 1980s. They commonly occur in the Azov, Black, and Caspian Seas, but they were introduced to North American waters through the ballast water of ocean-going ships. By the 1990s, over 20 states have reported zebra mussels, and the figure on the right shows that they've really proliferated throughout U.S. waterways in the decades since. They've become established in Mississippi, Missouri, Ohio, rivers, as well as many Great Lakes and smaller Midwestern lakes, ponds, and tributaries. They selectively filter, feed, and compete with native species and reproduce quite quickly, producing free-swimming veligers, and are often aided in their establishment and proliferation through the movement of human-made vessels such as boats and fishing equipment. So zebra mussels have a severe impact on native ecosystems and industry. They can biofoul a range of human and natural things. In this case, on the left, we see the intake pipes of a water treatment plant. We see the propeller of a boat, and then the establishment of zebra mussels on the surface of that crustacean. So it poses the question, how can one effectively and efficiently remove billions of zebra mussels from U.S. waterways? Well, one approach has been to make use of a substance called Zequanox, a trade name that is given to a bacterium extract, you could say, referred to as CL145A, which was discovered in the 1990s as a soil strain of bacteria with toxic effects on zebra mussels, specifically by destroying their digestive lining. At the same time, it remains naturally occurring, just a form of soil bacteria, but it also is safe for use among non-target species. In 2007, Marone Bioinnovations licensed this bacteria strain and formulated a mixture referred to as Zequanox, a suspension of many different components, with the active ingredient being spray-dried bacteria mixed with various inert carriers. In 2014, the EPA approved use of Zequanox in open water bodies, and is currently used to treat industrial and municipal water intake pipes. So Zequanox can be applied in the open water, and the equipment designed here was intended to serve that purpose, but it has to be spread near the benthic layer at the bottom of a fluid water body, and then it gradually diffuses to fill the water column and treat at least most of the regions affected by zebra mussels. These are figures showing its gradual dissipation or diffusion at various temperatures, showing how the concentration of Zequanox varies as a function of temperature and height, as well as sampling time. The equipment described here is essentially a water-going vessel, that is to say, Zequanox mixing and distribution equipment placed on top of a small barge of sorts and used to inject into the lower regions of the water bodies. So what this figure depicts is a cone used to pour Zequanox from the stand up above it, used to collect it and then funnel it down into the mixing chamber, kind of not really shown in this figure. And then it's pumped through a fluid network where it eventually sent into this tank for continuous agitation because it is a unstable liquid, and some settling and stratification will occur if it's not continuously agitated. And then it's sent through a pump and then injected into the floor of a pond through this injection nozzle shown here, which essentially injects a horizontal paper-thin stream of Zequanox mixture into the floor of the water body that's to be treated. So several challenges arose in developing the machinery and manufacturing process of the system. On the one hand, it had to efficiently apply Zequanox suspensions to the floor of ponds at varying depths. We had to minimize air entrainment in the mixture to ensure negative buoyancy, that is to say, it sinks to the bottom. We had to select equipment that minimized the risk of electrocution. We also had to minimize turbulence at the injection site. So we had to arrange the flow rate of the Zequanox to match that of the velocity of the boat in such a way that they provided a net zero velocity on the bottom of the pond. The Zequanox layer had to attempt to be 0.75 millimeters in thickness and distribute a uniform layer around a 0.75 acre pond before returning to shore to refill. The application width was limited to 12 feet, and it had to ensure consistent and controllable concentrations around 15 to 25 grams per liter, or we'll say just percent weight to volume as shown there, and maintain a lethal active concentration of 100 milligrams per liter for up to 8 hours, while also accommodating varying water temperatures and maintaining a homogeneous suspension of particles near the benthic layer of the pond. So the first set of challenges kind of discussed up above, and then I'll kind of describe the remaining challenges and the subsequent portions of the recording. So among the first challenges are to locate mixing devices that can minimize air intake and thereby minimize buoyancy in the mixture itself to ensure that it sinks to the bottom of the enclosure. And among the few mixing devices that could do this was the Quattro Liquids Ytron ZC1, which is used to mix chocolate in various chocolateries. And it breaks down cocoa powders and avoids entraining air, which would make the chocolate overly bubbly. It had a reasonable power draw, 64-inch height, completely homogenizes the material and minimizes air entrainment while also meeting the safety concerns. The trouble is that all models are electric, and it raises the risk of electrocution for use on vessels that are actually moved across the water. So, high voltage on open water or a boat is of great concern. The amperage actually gets through the skin is what's dangerous. Skin resistance can be as high as 1,000 ohms, but that drops when the skin is exposed to moisture. And a lethal amperage placed across the heart can be as low as 10 to 200 milliamps, kind of illustrating the threat that high voltage electricity would pose to people working on the Zequanox distribution system. So the initial design proposed to do everything on the boat itself, to have bags of Zequanox mixture placed in the storage container to be lifted up and poured into the hopper where they're funneled down to the high shear mixer for distribution into the storage tank and then injection to the floor of the pond. But the electrocution risks proved so concerning that an adaptation of this design was made to accommodate two boats and an onshore mixing site for the mixing and distribution of the Zequanox material itself. So in this case, we would have our storage containers with the Zequanox, pour it into the high shear mixer, agitate it, put it into a suspension and into a continuous agitation storage tank, whereupon when it's needed, it'll be pumped over to the storage tank on the transfer boat, which is a gasoline-driven boat with a gasoline-powered pump to maintain continuous agitation within the storage tank, and then send it over to the storage tank on the actual injection vessel, wherein it is again continuously agitated to maintain the suspension, and then administered to the floor of the benthic layer at the appropriate volume flow rate needed to perform the task. One of the challenges of this proposal was to provide a uniform distribution of about 0.75 millimeters thickness at variable depths and in a paper thin layer. So on the one hand, the manifold itself was restricted to 12 feet wide, and on the other hand, the expected velocity of the boat itself would be 1 to 2 miles per hour. So several iterations of injection manifold designs had been made. This illustrates one of kind of the many designs. Another one is illustrated here, where a variable aperture device was developed using concentric cylinders of polyvinyl chloride, shown in the white right there, and then steel on the interior with grooves machined into the surface of the materials such that the PVC layer could pivot clockwise, counterclockwise, and vary the aperture area depending on the pressure within the fluid rail and the velocity of the boat itself. So in this case, it would have been a combination of stainless steel and PVC construction with cam and groove connections, capped ends, and adjustable outlet layers to provide a uniform velocity, uniform Zequanox layer at a net zero velocity of the injection velocity with respect to the boat velocity. These then are various perspectives of that second design, but a third design was actually eventually settled on for ease of construction and installation. In this case, you can see upwards of 12 individual injection nozzles, 2, 4, 6, 8, 10, 12, distributed along the width of the injection manifold, shown there, that is to say over 12 feet area. And the intent with these nozzles was to allow us to forego the concentric cylinders shown in the preceding slide and actually make use of the momentum of the Zequanox water mixture to provide a fairly uniform distribution of Zequanox over the surface, which would then settle down and diffuse over the course of several hours. So several considerations had to be made. On the one hand, we had to make use of equal length hoses to provide a uniform pressure drop from the distribution manifold to the injection manifold, kind of this large one shown there. And with the equal lengths, it meant similar head loss, which would result in similar volume flow rates, whether the nozzles were on the periphery or near the center. Provide pretty uniform layer injection. This then is a depiction of the assembled full-scale model, showing the distribution manifold, wherein the Zequanox water mixture is pumped in through this 3-inch diameter hose, and then distributed among smaller hoses to the 12 injection nozzles shown there. And here we see this non-Newtonian fluid, which had the consistency of rather liquid pancake batter, actually injecting at pretty uniform flow rates as evidenced by the parabolic trajectories of pretty consistent profiles shown by all 12 injection nozzles. So the injection manifold was designed to have a range of 2 to 25 feet. That is to say, using winches, it would be able to be lowered down to a depth of 25 feet if necessary to treat the lower area of a particularly deep pond. It has a minimum depth range of 2 to 25 feet. We use steel square stock, 6 by 6 inch guide tubes, and 2 by 2 inch rails. So here's our 6 by 6 inch guide tubes and 2 by 2 inch rails, which allow the system to be lowered to 25 feet or so. We also used an assembly of rollers to ensure relatively low friction repositioning and raising and lowering of the equipment itself. Additional features included springs to prevent accidental damage. Right here, if the bottom of the injection manifold were to bump a rock, the spring shock absorbers would essentially avoid bending the 2 by 2 inch raising and lowering rods. Integrated depth finder to maintain the labeled lake bed offset, and then a control panel which allowed us to control the winch, the depth finder, and the flow meter for single kind of central control of the distribution system. So the design itself met many of the challenges kind of outlined in the initial statement of project design considerations. Beyond that, providing consistent concentrations, maintaining lethal concentrations for up to 8 hours, varying the suspension to different water temperatures, and then maintaining homogeneous suspension of the particles were additional concerns. So, as I mentioned, the onshore mixing equipment allowed one to use the high shear mixer, shown by the hopper here, the motor spinner shown there that infuses water in Zequanox together and then sends it into this storage container. This fluid circuit was designed for continuous agitation of the Zequanox mixture. This is just kind of a high-level schematic of how it is that the whole system works. Power going into the high shear mixture, Zequanox going into that, it being sent into the 275-gallon ICB tote, sent through the trash mixer, and put into continuous circulation, at least while it's being used or being mixed on shore before transferred to the transport vessel. Thereafter, a ball valve can be switched and the mixture can then be pumped onto the transport mixture. This shows as well that raw water from the lake comes in and provides the fluid for the Zequanox mixture. This is a kind of overly simplified depiction of the transfer boat, just again showing a similar type of fluid setup, in this case without the high shear mixer, but with a on-boat pump to provide continuous circulation to maintain the Zequanox water suspension. Again, the fluid system is fairly straightforward. The onshore mixture comes in. It is sent through a continuous loop as the transportation boat moves to the administration boat, whereupon it then sends the mixture out to the application barge for actual application to the subsurface benthic layer. Upon receiving the Zequanox mixture into the boat, then it is also maintained in continuous circulation, at least as necessary, and then this valve right here allows it to be redirected into the distribution manifold and then spread across the injection manifold in such a way that the volume flow rate can be controlled and one can establish a uniform velocity that is equal and opposite the velocity that the boat is traveling at. So again, continuous circulating mixture received from the transport vessel, which can then be redirected using a two-way ball valve through to the injection manifold previously. So the reconfigured design, which reduces the risk of electrocution substantially, contains 3 intermediate bulk containers, all around 275 gallons, suitable for a certain range of treatment. It also requires a transportation vessel and an application barge, but again, these are all to reduce the risk of electricity. Its beneficial features are that it's low cost, readily available, and interfaces with a range of coupler fittings. The onshore mixer uses an intake water pipe and a high shear mixer. So this is the intake water pump sending fluid to the high shear mixer. This is the Zequanox in dry powdered form that is then sent through the high shear mixer with minimal air entrainment to maintain the negative buoyancy that is so critical for this project. It also features low cost, ready availability. Then the transportation vessel and the application barge are both gas-powered, basically readily available equipment, low cost, and easy interfaces with the coupler fittings, and probably most important of all, it don't present a risk of electrocution. Finally, the fluid network had to be reasonably complex to maintain the appropriate concentration as well as maintain the suspension. So this is just kind of a quick high-level view of the application pump showing the piping and the portions of control valves and pumps needed to maintain the suspension. So many calculations or much time went into calculations concerning what volume flow rate would be necessary to provide a certain concentration at a certain application concentration at various boat velocities of 1, 2, and 3 miles per hour. So this is essentially a schematic showing how it is that volume flow rate would have to be adjusted depending on the boat speed itself. In addition to that, we have the two gate valves, one ball valve, raising and lowering mechanism, and a flow meter in place to show the instantaneous volume flow rate of the Zequanox mixer going into the pond itself. This then is an illustration of students manufacturing the actual Zequanox injection system. In this case, we see the 6x6-inch guide rails being welded together at the time, and the mock-up, or the frame, kind of being assembled at this point, including some of the supplemental components necessary. This illustrates the manufacturing of the distribution manifold and its testing using water in the parking lot at UW-Platteville. Then we actually did the mixing of the Zequanox with water, giving it this more milky color, characteristic of pancake batter, albeit kind of in a wet state. This figure actually. So some depiction of our method of control and the pretty uniform velocity of the. When the assembly was finally put together, the raising and lowering rails actually stood upwards of 25 feet in height, reaching the third story of the engineering building on campus. And it was installed on top of a barge provided by US Geological Survey. The figure on the right kind of illustrates some of the students actually putting it together. And this figure shown here illustrates the nearly complete assembly with the large vertical rails actually folded down, another feature of the design that ensured ease of transport and especially ease of access to areas that may have low bridges or overhanging trees. The total cost, at least in terms of materials, was just over $6,000. And a number of students, actually 3 separate teams, made individual contributions to the project, all of whom deserve some thanks, not only from myself, but from colleagues at US Geological Survey, including James Luma, the one who originated the project, Jeff Meinertz and Mark Gaikowski, some administrative people at US Geological Survey, as well as several people at Wisconsin WISIS, the tech transfer office for the UW system. This then is a depiction of 8 students and myself showing the final assembled portion of the Zequanox injection boat, and it was subsequently tested the summer after the semester was complete.